and Geological Engineering at the Colorado School of Mines. And moreover, he is also serving as the vice president for our ARMA. Okay, so thank you, Gabriel, for accepting our invitation, and it's your time.
Okay, thank you, Yao. I'll get my presentation pulled up here. All right, should be good to go. So thank you everybody
Right.
for coming here. My name is Gabe, and I'm going to be presenting basically some work that my group's been doing on rockfall hazard over the past decade that I've been working here at Mines. I want to take a moment right off the top to acknowledge all the members of my group who have contributed to the work that I'm going to be presenting today, and you can see their names here on the title slide. So the title is Modern Strategies for Characterizing and Forecasting Rockfall Hazard. And there's two keywords there, characterizing, which is really saying something about what rockfall hazard looks like today, and then also forecasting, which sort of implies that we're making some sort of prediction about how that hazard might change into the future. And so I'm going to talk a little bit about both of those. Now, in this presentation, I'm going to be talking about rockfall hazard in the abstract, really. But I want to start by acknowledging that there are some real concrete consequences when rockfalls occur. You can have destruction of property, as we see in this case. You can also have injuries or fatalities. Thankfully, in this particular photo, there was nobody in the car when it was crushed, but still obviously something you'd like to avoid if possible. And then you can also have sort of larger scale damage to infrastructure. This is a photo from Colorado where rockfall actually damaged a bridge deck. Um, and in addition to this sort of direct damage, you also have indirect costs associated with this. There's a particular stretch of highway in Colorado that's prone to rockfall. And when rockfall closes the highway, that turns what would normally be a 10 or 15-minute drive into a 4-hour detour. So that has direct or indirect impacts on the roadway users and economic impacts in terms of interstate commerce. Now, I've showed examples from Colorado, but this is not just a Colorado problem. This is sort of my anecdotal data that I'm putting up here. This is from my memory, states that have sent their Department of Transportation representatives to the Rockfall committee meeting at the Transportation Research Board conference over the past 3 years. And we can see that it's not a coincidence which states are sending people to this conference. They tend to be located in areas where we have mountains. We have a lot of mountains in the western U.S., and then, of course, the Appalachian Mountains out east. And the presence of mountains tends to be highly correlated with the occurrence of rockfall. I'll also note that this is not a comprehensive list of all the states that have notable rockfall hazard and risk. These are just the ones that prioritize sending folks to this particular conference. So with all that in mind, the motivation for all the research that we've been doing here at Colorado School of Mines on rockfall is basically how can we better characterize and forecast rockfall hazard than what we've done in the past. And so to start off, you need to put yourself in the DOT's shoes. Where do you start if you don't have any information about sort of the hazard in the state that you're managing? And of course, the first thing to do is to develop an inventory, right? Where are all the slopes that might be relevant to consider? And then also to develop a sort of relative prioritization of which slopes need the most attention, where the hazard is greatest. And for this type of thing, this relative prioritization, doing a semi-quantitative assessment is very common. And so many different states and organizations have their own rockfall hazard rating systems, which are these semi-quantitative systems. This is an example of the system that's used in Colorado. And it's semi-quantitative because basically you're looking at a bunch of variables. You are assigning them into categories based on the descriptions provided. And then based on the categories, there are point scores that get assigned. And then you total up those point scores for all the different categories to get a final hazard or risk rating. You can see if you look on the left-hand side, there are different factors that are considered, such as characteristics of the slope itself, characteristics of the climate, where the slope is located, and a lot of factors related to the geology. So this is a really great way to do sort of an initial relative prioritization, but there are a couple of key limitations. First of all, this is, of course, subjective. Some categories are easier to assess than others. And both as a result of that and also just as a result of the way these systems are designed, it can only give you a really coarse prioritization. So yeah, it might be good for separating your slopes into, high hazard, medium hazard, low hazard, but within any one of those categories, you're not getting very much granularity. And then importantly, even though you get a number out at the end, you're not actually getting truly quantitative data. And so if you're trying to do a quantitative risk assessment, for example, where you can directly compare the potential benefits of risk mitigation to the potential costs, you simply can't do that with this type of system. So ultimately, the goal is to try to come up with a more quantitative way to directly assess the hazard. And the first order controls on the hazard are basically how big are the blocks and how frequently are they coming down off the slope. So where can we start to try to assess that in a sort of practical way? Well, one way to look at that is to look at the in situ fracture network and try to relate that to the rock falls coming off the slope. And so we can imagine that we have a slope where the pre-existing fractures form blocks, and then over time, some of those blocks are going to detach from the slope and release as rockfall. And then, of course, when the blocks impact the ground, we have some fragmentation. Now, based on this, there's sort of a basic assumption that can be made, which is that the volume of the in situ fracture bounded block is exactly equal to the volume of the rockfall. That basically all rockfalls that are occurring are simply the release of blocks that already exist. There's no new fracturing going on. And then if we were to go and inspect the debris in a ditch or at the base of our slope, we would see that the volume of the blocks of debris would be strictly less than or equal to the volumes of the actual rockfalls when they detached. Now, there's quite a few studies that have gone out and compared the debris volumes to the in situ block volumes, because both of those are pretty easy to go and observe and measure directly. And what those studies find is that depending on the slope, the distribution of volumes of the debris tends to be smaller than the distribution of volumes of the in situ blocks, just like we would expect. But there's actually a surprising dearth in the literature of evidence to directly compare the actual released block volumes from the in situ fracture bound block volumes. And so that's something that we've been working on recently, is to try to directly compare these two things. And so I'm going to show you a plot here. We're going to talk about this plot in greater detail later in the presentation, so I don't want you to worry about the details. But basically what this plot is showing is, in the red line, it's the distribution of rockfall volumes. And then the green line with these blue and black linear sections overlaid, that is the in situ fracture bound block volumes. And essentially the takeaway here is that while there's part of the volume distribution that the rockfall distribution matches the in situ block distribution, there's also part of there's a range of volumes for which that is not true. And so we cannot sort of universally assume that the distribution of fracture-bound blocks on the slope is going to describe the rockfall volume distribution. If you're interested in learning more about this, paper 434 at this year's ARMA is going to talk about this some more. But, we can't make that assumption. But even if we could make that assumption, it's also important to keep in mind that we're just talking about the relative distribution of block sizes. This type of approach, even if we could trust it, still would tell us nothing about the absolute frequency of rockfall that's occurring on the slope. So we need a different type of approach to try to get at that. Now, aside from just strictly looking at the block volume distribution, you can use some more nuanced field assessment techniques. BGC Engineering developed a field-based hazard assessment protocol designed to do this. That's pretty interesting. I'm not going to go over this in detail, but essentially it involves a user estimating the relative frequencies of large versus small rock falls, and then the absolute frequency of how often rock falls are happening overall. And then that's sort of merged or averaged with a literature-based estimate of the expected rockfall frequency distribution to give you an output. And when we look at this, there was a paper in last year's ARMA by Kira Worley where there were 3 different inspectors who applied this at multiple sites. That's what you're seeing in the figure here. And one takeaway was, hey, the inspectors are pretty consistent. So even though this system involves some subjective judgment on the part of the user, we're not getting a lot of sort of uncertainty or variability based on that. So that's a good sign. But when we look at how much the inspector-based assessments varied between different sites, we can see that the inspector-based assessments were basically predicting almost the same rockfall distributions and frequencies at all the sites, whereas the actual observed rockfall distributions and frequencies were quite variable between sites. So, this type of field-based approach, while there are opportunities to improve it, and I believe BGC is working on that currently, it's still not at a point where, we can necessarily trust it to give us precise hazard information. So I think, many of you may be able to see where this is going. What about using monitoring as a way to assess the hazard? And when we think about monitoring historically for rock slopes, it's traditionally been limited by cost and, importantly, resolution limitations. And what I mean by that is that the traditional approach might be to go out and put individual point sensors out on the slope, like a crack meter or a strain gauge or something. And of course, unless you can predict exactly where the rockfall is going to happen, that's not necessarily going to be super useful for you. So there's been a big transition over the past couple of decades towards using point cloud-based methods, specifically LiDAR and photogrammetry. And, these are now practical and non-cost prohibitive tools that can be used for rock slope monitoring. So that brings us to sort of the core of our monitoring-based research program here at the Colorado School of Mines. It's been funded primarily by CDOT, starting in 2016. Since that time, we've been monitoring on a regular basis, multiple different slopes. We started off with just a few, and now we're up to 9 that we're regularly tracking. Something that I'm not going to talk about a lot today, but that is really critical to the work that we've done is development of advanced data processing and analysis tools. It's become easier than ever to collect huge volumes of data, but of course, unless you're able to do something with it, you're not going to get any useful information from it. And so earlier on, say in the first 5 or 6 years of this research program, we spent quite a lot of time working on implementing, adapting, and improving existing methods for semi-automated data analysis that have really enabled us to get our data processed in an effective and efficient manner. But ultimately, what I'm going to be talking about today and where our focus has been recently is this goal of quantifying or characterizing and forecasting the hazard and risk at these various sites. So on the left-hand side here, you can see a map of Colorado with the 9 sites that we're monitoring now. Not surprisingly, because this is funded by the Department of Transportation, these are all along highways. On the bottom right, you can see information about all the data that has been processed as of last year and the data that I'm going to be presenting in this presentation. So each one of these represents a different site. You can see that although we're currently monitoring 9 slopes, we only have enough data that it's sort of worth presenting 7 of them. And if we focus on any one of these, we'll look at Floyd Hill or FH here. We can see the extent of the data that's been processed. So here we have about 6 years of data at Floyd Hill. And then the vertical black lines show you when we have collected data. Every single one of them represents somebody going out with a tripod-mounted laser scanner like the one shown here and collecting data at the site. We can see that at Floyd Hill, for example, we've had some variability in our data collection. There's a pretty notable gap here in 2017, but generally speaking, we're monitoring sort of at least once a month from 2018 onwards. These sites here, we're monitoring about once a month. At this site here, it's twice a year, and twice a year is kind of the minimum frequency that we go out and collect data. Now, when we see these two here, IS, which is Idaho Springs, and MS, which is Manitou Springs, there aren't any vertical black lines. So you might say, well, Gabe, when are you collecting the data there? Well, with these, we're actually monitoring using a fixed photogrammetric monitoring system. You can see what one of the monitoring or camera stations associated with that system looks like here. This is at the Manitou Springs site. And basically, these systems consist of multiple fixed camera stations that are permanently installed that are taking photos every single day. We could theoretically do this at whatever frequency we wanted, but we've selected once a day as our monitoring frequency. And so we have sort of pseudo-continuous data at these two particular sites. Now, I mentioned before, I'm not going to get into the data processing in any big level of detail here, but I do want to just give you an overview to give you a sense of what we're doing. So when we get our raw data, on the photogrammetry side, the first step is actually to convert the photos into a 3D photogrammetric model, which is our point cloud. With the LiDAR monitoring, we start off with a point cloud. And the very first step, and probably the most important step in the whole thing, is this alignment, or it's sometimes called registration stage, where we basically need to take, in the context of the LiDAR, different data from different scanner positions and merge them into a common coordinate system. And then additionally, we need to, if we're trying to compare two different dates to see what's changed on the slope, we then have to put the point clouds for those two dates also into the same coordinate system so that we can make direct comparisons. Once we've done that, we then compute the change that's occurred on the slope. We use what's called the M3C2 algorithm, which is commonly used for this type of data processing. And then importantly, when we calculate that change, there are going to be regions where there's a big change that might, for example, correspond to a rockfall detachment. And then there's going to be other areas where, the apparent change between the two data sets is very low, on the order of whatever the noise in the data is. And so once we're at this point where we have change computed for every single point, we then filter out all the points where the change is negligible. And what we're left with is just points that correspond to where a significant amount of change has occurred. When we have that, we can then use a clustering algorithm to basically identify the spatial relationships between those points that have changed and say, hey, right here, this is one distinct spatial cluster of points that probably correspond to the same change phenomenon that's occurring on the slope. Importantly, so dbScan is the clustering algorithm. This and filtering is also very important because not all of the apparent change on the slope is actually going to be rockfall. Some of it might be real geomorphic processes that we're not interested in for our particular studies, like talus movement, for example. Some of it may be real change that isn't really relevant to the rock slope at all, like vegetation growing or dying over time. And some of it may not be real change. It may be, an area of anomalously high alignment error that, leads to an apparent region of change. And so for all of the data that you're seeing here, we don't just accept the raw change clusters. There's a hardworking grad student that goes in and manually reviews all of the clusters and sort of determines which ones of these are rockfalls and which ones are not. And then for each of these clusters, once we have a set of points that are associated with each other, we can then basically mesh an enclosed solid and estimate the volume of the rockfall from that. So this gives you a sense of what, just visually, what one of our databases looks like. This is at our GW or Glenwood site, just east of Glenwood Springs in Colorado. And this is just a subset of the full database. So we have, almost 5 years of data at this site, I think. But here we're just looking at a little over 2 years worth of rockfall. And you can see all the gray areas, that slope where rockfall didn't occur during this time period. And the red areas are where we detected rockfall. So we've done our processing. We have our databases. How do we use this for hazard assessment? And to explain this, I need to give you a little bit more background on some of the curves that we've been looking at so far. So what we're going to do is we're going to start by making a plot where on the horizontal axis, we're looking at the log of the rockfall volume. And on the vertical axis, we are looking at the log of the complementary cumulative frequency. So I say complementary cumulative frequency because it's telling us the frequency of rockfall volumes greater than or equal to a given volume V. And so when we plot that up, we tend to see that we have this sort of negative relationship where when we look at larger rockfalls, they are less frequent. And when we look at smaller rockfalls, they are more frequent. We also tend to see that this trend is linear over most of the range of volumes that we observe. But at the smallest volumes, we tend to have what's called this rollover effect, where there's this deviation from linearity in the log-log space. And that's typically associated with, or interpreted to be associated with, the fact that over a certain range of volumes, we are able to identify some of the rockfalls that happen, but not all of the rockfalls that happen. Basically, this is sort of like a gray zone for our resolution. Below here, we don't identify any rockfalls. Above here, we identify all the rockfalls, and in here, we're identifying some of them. Now, if this sort of linear trend in log-log space looks familiar, that's because we see it for a lot of natural phenomena, perhaps most notably, the Gutenberg Richter relationship for earthquake magnitudes, and we see the same type of thing for microseismic activity in a variety of contexts. But mathematically, this is described by a power law, which is basically saying that the cumulative complementary cumulative frequency for any given volume is equal to a constant multiplied by the volume taken up to this negative exponent. And so this constant in front of the V is very important because it basically represents the vertical position of this line on the graph. So for a given B, for a given exponent B, if we increase A, then we are saying that every single rockfall volume is becoming more frequent, is becoming more likely. And if we decrease A, we are saying that every single rockfall volume is becoming less frequent or less likely. And then our exponent B describes the slope of the line in this log-log space, where if we have a larger value of V or of B, we're going to get a steeper line, which corresponds to a higher proportion of small rockfalls relative to large rockfalls. If we have a lower value of B, we are going to get a larger proportion of large rockfall volumes and not disproportionately so many small volumes. So when we plot up this data for our data set in Colorado, we can see that we have some variability between our slopes. These are the 7 slopes that I highlighted before, and we can see that, just comparing, for example, at a volume of 10 to the negative 1, so 0.1 cubic meters, which is, if you're thinking about a cube, it's a couple of feet, a little less than a couple of feet to a side. If we look at that volume and we look at the frequency at different sites, we can see these are varying by over 2 orders of magnitude. And so, okay, that's quite a lot of variability in terms of overall rockfall. But when we dig into this, what we actually find is, well, the slopes that are smallest have the least rockfall, and the slopes that are largest have the most rockfall. And that kind of makes sense, right? For a given level of sort of intrinsic hazard at an individual slope, if you monitor an area that's 10 times as large, you're going to see 10 times as many rockfalls. So importantly, to look at this, we need to normalize by source area. And so now, instead of looking at cumulative number of events per year, we're going to look at cumulative number of events per year per hectometer squared, which is just 10,000 meters squared. And when we do this, we can see that we now have these curves that are basically representing quantitatively the rockfall hazard at the site. All the information about frequency and volume is incorporated here. The first thing to take away is that the slopes of these lines are actually relatively similar. There's some variability, of course, but the bigger difference between these different lines, between these different slopes, is their vertical positioning. It's that overall activity constant. And when we think about that, we can see that these 5 slopes here are somewhat grouped together. Now, again, there's some variability in here, but they're all within just under 1 order of magnitude variation in the frequency of rockfall that's occurring. Well, perhaps not coincidentally, these are all of our crystalline rock slopes. So all 5 of these are composed of igneous or metamorphic rocks. And then up here, we can see that we have these 2 slopes, Vail Pass and Manitou Springs, that are pretty consistent. And in fact, those are our 2 interbedded sedimentary rock slopes. They both consist of basically competent layers of sandstone that are interbedded with these weaker layers of shale. And so relative to some of the methods that we looked at earlier that are more based on field inspection or something like that, we could actually get closer to the true rockfall frequency volume distribution by looking at this chart and basically for any given slope, at least regionally within Colorado, finding the best analog, right? So if we go out to a new slope in Colorado, we're probably going to get closer to the true hazard if it's an interbedded sedimentary cut, similar to Manitou Springs or Vail Pass, by just adopting this hazard curve than if we were to try to make some field observations. Now, admittedly, we have 7 sites, and in the context of comprehensive sort of monitoring-based studies, that's a lot of slopes. It's still a pretty small sample size overall, and so we wanted to go a step further than this and try to leverage the broader set of data that exists in the literature. So my former master's student, Cam Phillips, went ahead and compiled a database from the literature, including 34 different sites from around the world. What you're seeing on the left-hand side here is basically those power law fits for all of the different sites. He originally was looking at data from terrestrial remote sensing, similar to what I've been talking about so far. He also looked at some satellite-based databases and databases based on measurement of block sizes at the base of the slope. But what he found was basically that because of fragmentation in the case of debris measurement, and because of essentially resolution issues in the case of satellite or aerial monitoring, was that there were some pretty consistent biases in those estimates relative to the terrestrial remote sensing approach. And so for his statistical analyses, he focused strictly on the terrestrial remote sensing data that he'd pulled from the literature. And you may have balked earlier when I said, well, these 5 crystalline slopes are within less than an order of magnitude in terms of in terms of their vertical position. Well, that is actually relatively close compared to what we see worldwide. We can see that the least active slopes worldwide had a constant, an activity constant. This ST subscript is standardized. This is just meaning it's normalized to the area, as I was mentioning before. These least active slopes have an activity constant approaching 10 to the -2, whereas the most active ones have an activity constant approaching 10 to the 1.5. So even being within one order of magnitude is pretty close in the grand scheme of things. So with this database that Cam compiled, he did some statistical analyses, and I just want to highlight a couple of key influences on this overall activity constant that's controlling the hazard. The first is rock mass condition. Perhaps it won't surprise anyone that we saw that pretty clearly rock mass condition is assessed using standard rock mass characterization, shows a notable influence on this activity constant for rockfall. Specifically, we see that slopes composed of better rock masses have lower activity than slopes composed of worse rock masses. We also see that the effects are greatest once we get to the good or excellent rock masses. The difference between a poor or a fair rock mass is a little bit less notable. The other difference that I want to highlight here, even though it's not statistically significant if you look at the p-value, is the difference based on rock type, sedimentary, metamorphic, or igneous. We can see that there appears to be a bit of a trend towards these crystalline rocks exhibiting lower rockfall activity than the sedimentary rock slopes. But from a practical perspective, it's hard to really pull anything from this because the sedimentary slopes also have a huge range of variability, right? So if you go out and look at any given sedimentary slope, okay, yeah, the activity is probably higher than some nearby crystalline slope, but there's a good chance it may be incredibly low activity as well. And, in talking through these results with Cam, we kind of decided that part of the issue here might be that the sedimentary classification encompasses such a broad range of possible rock mass conditions. And so he ended up splitting it out where we split the sedimentary category into bedded sedimentary rock masses, like the ones that I was describing earlier at the Vail Pass and Manitou Springs sites in Colorado, and then massive sedimentary sites. And you can think of this as, massive limestone cliffs in Europe, or some of the massive vertical sedimentary rock exposures that you would see in Utah. And what we see here is that now we have a very statistically significant result where clearly these bedded sedimentary cuts, not just the two that we monitored in Colorado, but sort of worldwide, these bedded sedimentary cuts are consistently exhibiting a higher level of rockfall activity. So the takeaway here from this analysis was basically that just by thinking about your lithology and your rock mass condition, you can already get a pretty decent starting point for a quantitative assessment of the hazard at a given site. Obviously, would it be great to go out and monitor all your high priority sites with LiDAR or photogrammetry with high temporal resolution for multiple years? Yes, of course, that would be ideal. But even practically speaking, there seems to be some suggestion from these analyses that we can use these databases that we've developed as a bit of an analog for some of the other sites that we may end up studying. So that kind of covers the characterization piece. But what about forecasting future hazard? Well, in the context of geotechnical asset management, which is really this sort of philosophy or approach that's commonly applied in the transportation world, slopes are considered to be assets in the same way as, a bridge might be an asset to the transportation network, or a tunnel might be an asset. The slopes are considered assets, and they're considered to deteriorate over time. So in the same way as when you build a bridge, over time, the materials composing that bridge are going to degrade, and maybe the bridge is going to need some rehab after a certain number of decades. The idea is that slopes may behave in the same way, that the slope is going to get worse over time, and we may see more rockfall heading into the future. So in this context, when we're talking about rock slopes, the term deterioration is basically saying we're expecting that there might be some increased hazard over time. And right off the top, I want to say here that climate change is an obvious potential factor. If we're talking about rockfall hazard going up over time, there's a good chance that there are many areas in Colorado, in the US, and the world where climate change may lead to increased rockfall activities. But for the purposes of today's presentation, I want to focus on some other factors that we have done a little bit more work on so far. So Kira Worley, one of my master's students, put together this chart, which basically shows in a quantitative hazard assessment all of the different factors that may influence the hazard. And highlighted in the red are 4 factors that she considered in her thesis as potentially changing over time. We're not going to talk about ditch effectiveness today because it's maybe not the most rock mechanics focused piece of what she did. And we're not going to talk about scaling or rock bolting because those were some of the most data poor scenarios that she looked at. So instead, we're going to focus in on the MCF curve. So again, these are the curves describing the frequency and volume of rockfall. And we're basically going to ask, how would we expect this to change over time, not considering climate change? Before I can do that, I need to define a couple of terms. So the first is rockfall activity. So when we're talking about rockfall activity, we're talking about what the underlying hazard is, or what the underlying MCF curve looks like at any given point in time. And the reason why I say underlying is that if you go out and monitor over, say, the summer, you might get you might observe different rockfall trends than if you'd monitored for the whole year, right? So if you're only monitoring for part of a year, you're not getting at the underlying hazard. But even if you are monitoring for an entire year, maybe that year was a little wetter than most years, or maybe that year was a little colder than most years. And so that variability in sort of forcing factors also means that over an individual year, you're not necessarily getting at the underlying MCF curve. You really need to monitor for a longer period of time if you want to get at that. But I guess the point I'm really trying to make here is that, if we go out and monitor, and then we go out and monitor a few years later, and we see, the curve appears to have gone up, that doesn't necessarily imply that the underlying hazard has gone up. That may just be sort of variability in the curves. And so that variability may look like this from month to month or year to year. And then the other term is physical deterioration, and this would be consistent, coherent changes in the MCF over time. So not year-to-year variability, but a consistent sort of, for example, upward movement of this curve indicating increasing rockfall frequency over time. And with these 2 terms in mind, the activity and the deterioration, I want to really emphasize here that high deterioration is not the same thing as high activity or hazard. So you can have a slope that is low hazard, but it's getting worse quickly. You could also have a slope that is high hazard, but it's not changing at all over time. So with that in mind, we came up with a conceptual model that sort of tries to describe what we might expect to happen after we cut a brand new rock slope. The idea is that your freshly cut slope is not going to be very weathered. It's going to be nice, fresh rock. That's basically the strongest your rock mass is ever going to be. Now, there are going to be potentially some initial relaxation effects when you cut the slope and the slope is relaxing, releasing those stresses that were previously locked in. You may see for a few months a period of increased rockfall activity. But after that, we're at basically a minimum point for rockfall activity. So we're going to plot this up in terms of rockfall activity or hazard versus the time since we cut the slope. And if we look after the end of that relaxation period, we've got very fresh rock, freshly cut. We have a low level of activity. Now, if we imagine far into the future, we're now thinking in geomorphic terms, like say 10,000 years. At that point, the slope is going to be fully weathered. It will have reached a point where the weathering front within the rock mass has propagated pretty far deep into the rock, and the extent to which that weathering front it continues to propagate each year is approximately equal to sort of that erosion rate or the rate at which the slope is moving backwards each year. So we're in sort of a geomorphic pseudo-equilibrium here. And of course, when the slope is fully weathered, we would expect that we would have a higher level of rockfall activity than when it's been freshly cut. And so we can put a point out here. So that's all well and good, but what are we supposed to do with this, right? Well, we're not thinking from an engineering perspective about 10,000 years from now. How can we say something about what happens in between? Well, one approach would be to just draw a straight line here, right? But that doesn't really make a whole lot of sense because in reality, the fastest rate of weathering is going to be right at the beginning when the rock is fully fresh. Once the weathering front has propagated into the rock mass a little bit, it's going to get harder and harder for it to continue propagating further. And so we should actually expect a shape of our curve that looks something more like this. Now, this is better, but we're still stuck in a situation where, we don't know where this curve sort of starts to roll over. Does it become flat after 10 years, 100 years, 1,000 years, 5,000 years? We don't really know. And so to try to answer this question, we ended up partnering with the Washington Department of Transportation, who has a pretty detailed inventory and set of records associated with their slopes. Specifically, they have slope ratings, sort of similar to the semi-quantitative assessment that I showed you at the beginning. They have those slope ratings for 720 slopes through time. And so the idea is that we can look at these slopes and see how the ratings are changing through time. If the hazard is getting worse over time, we would expect to see the ratings getting higher, indicating higher hazard over time. So let's take a look at the data. Well, the first thing we can look at on the right is sort of the simplest way to visualize the data, which is simply for every single slope, we have one data point, and we're plotting the most recent slope rating against the age of the slope at the time it was rated. So if we were seeing a trend towards all else being equal, older slopes consistently having higher hazard, we might expect to see sort of an upward trend, an upward slope in the data here. And we really don't see that. We see quite the scatter shot here. And if you apply mathematical techniques, you can confirm that there's basically zero underlying slope here. Now, that's just one way to look at the data. We decided, well, we have more than one rating at each slope. Some of these slopes have been rated 2, 3, in rare cases, even 4 times over time. And so rather than just looking at the most recent slope rating, we can actually look at the trend over time separately for each individual slope. And that's exactly what we're looking at on the left-hand side here. Basically, we're looking at the average change in the rating per year based on a simple linear regression to the individual ratings for each individual slope. And then versus the mean slope age across all the ratings that were taken. And what we can see here is that most of the slopes are clustered right around 0. So when we look at the slopes individually, the ratings are really not changing over time. We do have a few slopes where there seems to be a consistent trend towards ratings getting higher, worse hazard over time. And there's a few slopes where we have a trend towards actually the hazard appearing to reduce over time. Now, some of this is inevitably going to be based on the subjectivity in the assessment, particularly if there was a difference in the inspector at a given slope between the first time it was rated and the second, for example. But overall, while we can't draw conclusions about any individual slope here, we can say that there's pretty clearly no systematic underlying trend across the entire suite of data. So what's our takeaway here? Well, I guess an important thing, I'll go back for one moment, an important thing to note is that if we look at these plots, we actually don't have data for slopes that were excavated, within 20 to 25 years before the ratings were taken. And so all we can really say is that there's no evidence of systematic changes in the rock slope condition beyond about 20 to 25 years after excavation. Now, that's not to say that there couldn't potentially be some changes from when the slope is first excavated to say that 20-year mark. To interpret this, it's important to sort of compare this to the timeline of scaling influence. So scaling is going out and manually removing potentially unstable pieces of rock. And there's some evidence in the literature that suggests that depending on how much scaling you do, that scaling may reduce the rockfall hazard for something on the order of 5 to 15 years. Now, if we think of that 15-year timeline corresponding to super intense scaling, where you're basically removing almost all the exposed blocks at the rock surface, that's kind of analogous to cutting a brand new fresh slope, right? And so in that sense, it's not totally crazy to think that if the effects of intense scaling are limited to a 15-year impact, that the amount of time it would take to weather a freshly cut slope might take a similar amount of time, say 15 to 20 years. So going back to this chart, our sort of preliminary suggestion is that maybe this sort of curve starts to level off after 15, 20, certainly 25 years. Again, I want to emphasize here, because activity and deterioration are not the same thing, this does not mean that old slopes can't be in bad condition, right? There's a lot of old slopes that are in bad condition that have very high hazard. What we're suggesting is simply that, for many of these slopes, there doesn't seem to be a lot of evidence that they've been getting worse over time. Maybe that, old high hazard slope also had its high hazard 20 years ago when it was only 60 years old instead of the 80 years old that it is now. I also want to clarify that this does not demonstrate that deterioration cannot occur beyond 20 to 25 years for some slopes. It's possible that some slopes behave differently from sort of the aggregate behavior that we're observing here. And importantly, as I mentioned at the top, this does not include consideration of climate change impacts, which we expect to accelerate into the future. The data, I guess I should say, sort of implicitly account for whatever climate change occurred over the time frame that these slope ratings were taken. But because we expect climate change to accelerate into the future, we can't be confident about what those effects are going to be. And we actually have some upcoming research projects that are going to focus on trying to evaluate that specifically. So to briefly summarize, point cloud-based monitoring provides rich data for analysis of rockfall hazard. When we have these data, we can identify what the key influence factors are, and then potentially we can generalize some of this information for application at slopes that we haven't been monitoring. And then our understanding of how slope hazard evolves through time is starting to become evidence-based, but this is where the least research has been done in the past, and there's a lot more work that's needed. So with that, I'll wrap up my presentation, and I would be very happy to take any questions that you might have. Thank you.
Thank you, Gabe. So any questions from the audience?
I've got a quick question. This is James McNabb. Great presentation, Gabe. I really appreciate it. Really interesting stuff. I'm curious, you have this really rich database of rockfall. You've got the spatial database as well as the temporal database. So I'm curious if you've looked at kind of that spatial distribution, relating it to geologic structure and so on. It's basically you've got these maps of rockfall initiation zones.
Yeah, absolutely. So, yes, we have looked at that in the context of individual sites, and it varies a lot. Most of our sites are actually relatively homogeneous geologically and structurally across the slope. So, at many of them, we're sort of seeing a roughly uniform distribution of rockfall. But there's definitely cases where, in some of the crystalline slopes, there's a more weathered area where there tends to be higher frequency and lower volume than some of the other areas, right? At the sedimentary sites, we see pretty consistently that you'll have small rock falls in the shale, and then you might have a bigger rock fall occur above that when the shale undercuts part of the sandstone block, right? So we definitely see those mechanisms. Where we ultimately hope to take that is trying to understand what predictive value those spatial relationships may have. And so I've currently got a PhD student working on a project to try to evaluate that, whether, there's coherent spatiotemporal relationships that could be leveraged to sort of forecast where on the slope the hazard of the next rockfall might be higher.
Yeah, fantastic. Thank you.
You're welcome. Great question.
Okay, I guess I'll go next. Thank you for the great talk, Gabe. I learned a lot. It's very interesting. So you mentioned, I have a lot of questions. You mentioned that there's a place off the highway, and then so you have these monitoring points at different places in Colorado. Why is I forgot. So it's MS orange line, and you have this similar trends with the purple line things nearby. But the orange line is off the highway. So what's the reason of having higher rockfall activities in those areas?
Yeah, so if I understand correctly, you're kind of getting at like the MS and VP sites where the lines
Yes.
were higher up.
Yeah.
So those are both along highways. VP is along Interstate 70, and then
Mm-hmm.
Manitou Springs is along, I believe it's US 24, if I'm not misremembering. And so, um, the rockfall hazard. What's interesting is that these are in very different sort of geographic areas. The Vail Pass
Yes.
one, it's literally on a pass up in the mountains, right? And the other one
Okay.
is sort of down just outside the town of Colorado Springs, very different elevations, some differences in the climate.
Mm-hmm.
Um, and yet they display very, very similar rockfall trends. And so there's two possible interpretations here, right? One would be well, these both have very similar geology, and geology is basically the key impact here, and that's why they're similar. The other interpretation would be, well, there could be some factors that are making rockfall want to be higher at Vail Pass, but then they're offset by other factors that are also changing, right? So there could be confounding variables in here that we're really not able to tease out with two data points. But essentially, you know, the I think it's reasonable to expect that geology would play a notable role, even if it's not the only factor, right? The meta-analysis sort of confirms that. And so in terms of why those two are higher rockfall activity than the crystalline sites, I would attribute that primarily to the geology. But again, that's an interpretation, right? That's not something I would say that we've definitively proven.
Yeah, I was looking at the map of the faults in Colorado. I don't know how far are those sites from the um, tectonic fault. I wonder if there are any effects on those
I would say
behaviors.
I would say that the faults are not close enough that there's an obvious effect on the rock mass structure. And then the other thing I would say is that we don't have a huge amount of seismicity, so that's also not a major factor.
Yep. Great. Thank you.
Okay, it seems like we have some comments and questions in the chart. We have several.
Yeah, I see Gowan has a lot of questions here. I'll
Yeah.
answer his first one in the interest of time here. It's a very good question, basically talking about accounting for ice buildup and melt and how much of the ice buildup contributes to rockfall hazard. So basically, we do detailed analyses at each individual site in terms of how rockfall trends vary through time. And so we have found, consistent with other studies worldwide, that at these Colorado sites, for the most part, we see a peak in rockfall activity sort of in the springtime when we have a lot of melt. Now, it actually varies a bit from site to site. Some of the sites, depending on their elevation, they may see the peak sort of early spring. Some of them may see the peak more like late spring. Some of them see the peak actually into the summer, getting towards, August even. In terms of like the overall aggregate effect, though, one thing I didn't present from the meta-analysis of the literature is that the only climate variable that we looked at that had a statistically significant impact on that activity constant was basically a measure of how cold the climate is, how much freezing occurs. Interestingly, though, that effect, if you compare the warmest site that was in the database to the coldest site that was in the database, the amount that appeared to affect the rockfall on average was not as large as either of the effects that I presented, the rock mass quality or the geology. So a notable effect, but not the most important effect. Maybe more of an important effect on the timing, as I alluded to before. Oh, there's a question here I saw. Can you comment on the application of this work to high walls, and have you considered collecting data from a mine? There is no real reason why you could not apply this to a high wall. We definitely are interested in opportunities to collect data in a mining setting. I think the reason why we have not, why that hasn't been our main focus, aside from the source of our funding, obviously, but it hasn't been a main focus because the technologies for high wall monitoring to be applied at that particular scale are pretty well developed using things like ground-based INSAR, for example. Those technologies are well established and work pretty well at that larger scale. So the sort of value added or marginal benefit of pursuing a point cloud-based approach like what we're using is maybe lower than in some of these smaller scale applications. Any other questions, Mangsu?
Gabe, so a question for the future. What do you think are the research opportunities for future on the intersection between rock slope stability, climate change, and geomorphology, and even subsurface geology?
Wow, that's a big question.
Sorry.
I mean, I think that I think there's a lot of opportunity in terms of collaboration with geomorphology, and I'll be the first to admit that I probably do not know as much about geomorphology as I should. I come from a geological engineering background, but in speaking to some of my colleagues who do geomorphology, I've learned quite a bit, and I think that geomorphologists tend to approach these problems from a different perspective, but there's probably some tools that could be combined or some knowledge that could be generated from that type of interdisciplinary collaboration. I think another big factor is that, how would I put this? I think I'm, in many cases, I would characterize myself as a slight AI machine learning skeptic in terms of applications in rock mechanics and geological engineering. And I think that's because in most applications, the variability is very large relative to the amount of data that we have access to, right? In this particular context, we're generating huge amounts of data. It may still not be enough to truly justify using these machine learning or AI approaches, but I do think that working with this type of data is one area where you know, it may be promising and merits some investigation. And so that could potentially be a way to learn some things about how those techniques can appropriately capture geological variability that might down the road be applied in different contexts.
Thank you.
Okay. Thank you very much. Thank you again for Gabe to give excellent presentation. And our next speaker seminar will be 3 weeks later, and will be the Wenfeng Li from the Los Alamos Lesson Laboratory. And I have sent our YouTube channel in the one who has interest in our past seminars could find the recordings. Thank you, everyone. Have a nice rest of the day.
Thank you.
Thank you.
Thank
Thank you
you
so much.